our first presenter, our first finalist, coming the whole way from Texas, is David Cohen. So David, how are you, my friend?
Great, how are you?
I am great. I am really excited about your presentation. I saw a little bit yesterday in rehearsal. Ready to go?
Yeah.
Knock 'em dead, my friend.
Thank you.
Round of applause for David.
Malaria kills 1 child a minute worldwide. It's a problem that desperately needs to be solved. My name is David, and today I'm going to be talking about preventing mosquito-borne diseases. Examples of mosquito-borne diseases are West Nile virus and malaria. Many control methods try to kill mosquitoes that are mature and can fly. These methods can be hazardous, expensive, require ongoing retreatment, and are not always effective. So my approach is purely physical and limits mosquitoes in their immature stages. So immature mosquitoes progress through 3 stages: eggs, larvae, and pupae. Now, the larvae and pupae require oxygen, and all these stages exist in the water. So my robot is designed to capture and destroy immature mosquitoes on the surface of the water. So I came up with a general design concept inspired by a pool robot for how my robot would work. My robot would pull immature mosquitoes underwater long enough to drown them. It would use a pump to reduce water flow, which would propel the robot and drown the immature mosquitoes. And it would have an inlet mesh to prevent larger objects from entering. So I went through several prototypes in this entire process. Generation 1, I built out of hardwood cloth and wood, and it failed because the hardwood cloth was too stiff and was hard to form shapes with. Generation 2, I built out of cardboard and fabric, and the cardboard was too flimsy, absorbed water, and sank. So unfortunately, it did fail. Generation 3, I built out of plastic and foam netting, and it failed because the plastic was too fragile and the holes in the netting were too small. Generations 4 and 5, I built it out of paper and plastic, and it failed because it was just very difficult to manufacture. Generation 6, I built it out of PVC and wood, and as you can see, it was a success. So I used 2 3M materials in my innovation: dual lock to suspend the motor within its waterproof compartment, and hook and loop to allow for easy battery changes. So in order to test my robot, I brought frozen larvae and defrosted them in some water. I then placed the larvae in the water with the robot I designed. So these are the larvae floating on the surface of the water. Now, as the propeller spins, the larvae are pulled underwater and kept there until they drowned. And at the same time, as the propeller spins, the robot is propelled forwards. After my robot ran for about a minute, I took a look at the mesh I installed for testing purposes, and dozens of larvae had been trapped by the robot. So I had a question: how long can larvae be underwater for? So in order to determine this, I contacted an expert in mosquito biology, and he suggested I breed mosquito larvae before performing the experiment. Once I had bred mosquito larvae, I disturbed the water continuously and measured the time until the larvae had returned to the surface. My results showed that larvae can be underwater for over a minute. And because of this, I concluded that a mesh that keeps them underwater would be required. So I knew I needed the mesh, and I was wondering how much will that affect the speed of the robot. So I hypothesized that the robot will move slower with a clogged mesh due to the resistance, the flow of water. And then using a stopwatch, I measured the time to travel a set distance. With the mesh, my average was 26 seconds, and without it was 17. So the mesh significantly decreased the speed of the robot. And because of that, I concluded that the mesh would have to be opened regularly to release the dead larvae. So there are several physical principles involved in my robot. Flotation is explained by Archimedes' principle of buoyancy, which states that an object will continue to sink until the weight of the water displaced is equal to the weight of the object. Propulsion is explained by Newton's third law, which states that every action has an equal and opposite reaction. Object capture, the ability to capture mosquito larvae, depends on drag, pressure gradient, and the vortex created by the propeller. And mosquito larvae use surface tension to hang from the meniscus, the surface of the water. So basically, mosquito larvae are air-breathing and will die if held underwater for long enough. That basically makes my robot possible. Okay, so in the future, I plan to add a solar panel, so there's no need to replace batteries, an automatic emptying mesh, better recovery from collisions, and better control over direction. So I want to thank Discovery Education and 3M for... Okay, you're welcome.
So David, thank you. I'd like to place an order right now for our backyard pond. But on a more serious note, if you think about the current design that you have today, can you think about any potential negative risks or environmental aspects that might be associated with this design? Could it impact other plants or animals or wildlife?
Yeah, so I haven't done much testing on that, but the robot does kill mosquito larvae, and there are fish that do eat mosquito larvae, so that possibly could affect them. On the other hand, the mosquito larvae aren't trapped in the robot. They're just let out at the end. So if the fish will eat larvae that are not alive, it would not affect them.
David, why was this topic of interest to you?
So I live in Texas, where we have a big problem with West Nile virus, and I was looking at, what's being done to solve this problem, and I noticed that many of the methods were trying to kill mosquitoes that are mature and can fly, and that can be problematic. So I was wondering, could you kill them on the surface of the water before they're even mature and able to fly?
Great design, David. Question. What is the cost value in terms of your design versus current methods like the biologicals versus synthetic pesticides?
Okay, so my robot, it costs about $25 to build. When mass produced, it could cost less. But on the other hand, I plan to add a solar panel, so that could about balance out the cost. So for my robot, you're thinking $25 to $30. So current methods, there are many. For example, a mosquito net. It's much more expensive, and it is effective. My robot isn't designed to replace any methods. It's just designed to help in the fight against malaria and West Nile virus. So yes, other methods are much cheaper, but it's possible that the positive impacts of this robot would account for that.
Thank you.
You're welcome.
Hi, David. What other tests could you possibly make, or did you possibly make, with the frequency that the robot has to pass in a given area to keep up with the rate of reproduction?
Okay, so mosquito larvae the minimum time for them to reproduce is 7 days. So the robot would have to return to the same spot every 7 days. So I calculated that 1/2 to 2 acres would be about the right amount of space for the robot to function in.
David, as far as the actual operation of the robot, is it controlled through a handheld device? Is it just put in motion and then operates on the lake or pond, wherever it is? How does it move around the area to capture the larvae?
Sure. First, it's important to understand what type of mosquito causes malaria. So it's the Anopheles genus of mosquito that causes malaria, and that genus is unlike most genuses because they lay their eggs randomly on the surface of the water. They're not grouped together in any configuration. So it would be more effective just to have the robot move randomly across the surface of the water, and that's exactly what it does.
Hi, David.
Hi.
So sort of a follow-up, does this work like a Roomba kind of thing where will it get stuck in one spot, or have you found that it actually can free itself and continue moving?
Yeah, so currently, yeah, it is like a Roomba. Unfortunately, it does have a little bit of problems with getting stuck, but I plan to add sort of a spring mechanism around it to prevent against that.
Hi, David. Great job. That was great. First, have you tested how long the battery in that thing would last? Like, would it be able to be recharged quickly enough by a solar panel?
So yeah, I actually haven't done much testing in that. I can tell you what kind of batteries it uses. It uses 8 AA batteries, alkaline. But I haven't. I measured with some looking at the voltage and current required by the solar panel, and it looks like it would be effective, but it might require more thinking and more problem solving.
Okay.
Thank you.
Hey, David.
Moving back.
Did a great job.
Thank you.
All right.